biasing. In forward biasing, the external voltage is applied across the PN junction diode. The forward bias means the positive region is connected to the P terminal of the supply, and the negative region is connected to the N type of the device. This voltage cancels the potential barriers and provides the low resistance path to the flow of current. If this external voltage becomes greater than the value of the potential barrier, 0.7 volt for silicon and 0.3 volt for germanium, the potential barriers opposition will be overcome, the current will start to flow.
This situation happens because the negative voltage pushes electrons towards the junction, giving them the energy to cross over and combine with the holes being pushed in the opposite direction towards the junction by the positive voltage. In the forward characteristic of a diode, once the voltage is applied, then the junction starts increasing rapidly. It is known as knee voltage, and an alternate name of this is cut-in voltage. When we apply voltage to the terminal of diode, the width of depletion region slowly starts decreasing. The reason for this is, in forward bias, we apply voltage in a direction opposite to that of barrier potential.
Reverse bias. In reverse bias, the negative region is connected to the positive terminal of the battery, and the positive region is connected to the negative terminal. The reverse potential increases the strength of the potential barrier. The potential barrier resists the flow of charge carrier across the junction. It creates a high resistive path in which no current flows through the circuit. The positive voltage applied to the N-type material attracts electrons towards the positive electrode and away from the junction, while the holes in the P-type are also attracted away from the junction towards the negative electrode.
The depletion layer grows wider due to a lack of electron and holes and present a high impedance path, almost an insulator. A high potential barrier is created, thus preventing current from flowing through the semiconductor material. However, a very small leakage current does flow through the junction, which can be measured in microamperes.
Transistor. The bipolar junction transistor has three separately doped regions and contains two PN junctions. Bipolar transistor is a three-terminal device: emitter, base, and collector. The base transistor principle is the voltage between two terminals controls the current through the third terminal. Current in the transistor is due to the flow of both electrons and holes, hence the name bipolar. There are two types of bipolar junction transistor, NPN and PNP. The NPN bipolar transistor contains a thin P region between two N regions. The PNP bipolar transistor contains a thin N region sandwiched between two P regions. The function of each terminal device is: first, emitter, to emit or inject electrons into the base; second, base, to control the current flow through the circuit; and the third, collector, to collect electrons from the base for use in the circuit.
Operations of NPN. Forward active mode. The base emitter junction is forward bias and the base collector junction is reverse bias. Since the BE junction is forward bias, electrons from the emitter are injected across the BE junction into the base, IE. Once in the base region, the electrons are quickly accelerated through the base due to the reverse bias CB region, IC. Some electrons, in passing through the base region, recombine with majority carrier holes in the base. This produces the current, IB. Operations of NPN. Forward active mode. The emitter base junction is forward bias and the base collector junction is reverse bias. Three regions of operation. Active, operating range of the amplifier. emitter forward bias, and collector is reverse bias. Cut off. The amplifier is basically off. There is voltage but little current. Both junctions reverse bias. Saturation. The amplifier is full on. There is little voltage but lots of current. Both junctions forward bias.